In this video we're going to look at coordination number and how it applies to covalently bonded molecules, transition metal complexes, metallic solids and ionic compounds. In a covalently bonded molecule, the coordination number is just determined by counting the number of bonded atoms. So each carbon in this molecule is bonded to 4 atoms, it has a coordination number of 4, which the carbons in this one are only bonded to 3 atoms, coordination number of 3. In this one, the carbons are bonded to 2 atoms, coordination number of 2. And finally, the carbon in this molecule is only bonded to 1 oxygen, and so it has a coordination number of 1. Notice it doesn't matter if those bonds are single, double or triple, we're simply counting the number of directly bonded atoms. We can also apply this to ions. The carbon in this carbonate ion is bonded to 3 oxygens, so it has a coordination number of 3. Transition metal cations form complexes by bonding to groups called ligands. The coordination number of the transition metal of the complex is again simply obtained by counting the number of bonded atoms. So this vanadium is bonded to 4 bromines, coordination number is 4. This cobalt has a coordination number of 6, it's bonded to 4 nitrogens and 2 chlorines. And this iron is bonded to 4 nitrogens, coordination number of 4. Notice that the 4 nitrogens are attached together in a big ring, but the coordination number is 4 because it's the number of directly bonded atoms. In a metallic solid, there are no clear bonds between pairs of atoms. The metal atoms are arranged as closely as possible in layers, and then these layers stack on top of one another. In order to obtain the coordination number, we must count the number of nearest neighbours. So here we have a layer of atoms, and our close packed atom has 3 below it. It has 6 around it, and it has 3 on top of it. So the total coordination number is 12. Another way of thinking about the structure of a solid is to use unit cells. Unit cells are the simplest building blocks which we repeat in 3 dimensions to generate the structure of the crystal. So here's a body-centered cubic unit cell. It's a cube with an atom on each corner and an atom at the center. And this brick is going to be repeated in 3 dimensions forever and ever and ever to generate the structure of the metal, the structure of the crystal. We want to work out the coordination number. So here's our unit cell. We're going to colour one of our atoms green and watch what happens to it. So at the moment we've got 1 cube. We place another one to the next door to it, 2 more below, and we still have space for more on top. So we're going to place 4 more on top, and that's going to hide our green atom. So we shrink our atoms and see that the green atom is surrounded by 8 metal atoms. So its coordination number is 8. In ionic solids, there are also no clear bonds between pairs of atoms. Now we have cations and anions packing together as closely as possible. And again we must look at the structure and count the number of nearest neighbours. So here's the sodium chloride structure. We have cations in red and grey chloride ions. Here's our unit cell, and like we did in the last example, that unit cell has got to be imagined as a Lego brick that can be packed, surrounded in 3 dimensions in order to work out the structure of the whole solid. So in order to work out the coordination number of our cation, we look at the number of atoms around it. There are 6 chlorines, and so the coordination number of the cation is 6. For the chlorine, we have to actually add another atom from an adjacent unit cell. So for our chlorine, we see that there are 6 red sodiums around it, so the coordination number of the anion is also 6. So in order to understand the structure of solids and to count coordination numbers, we actually have to look at the crystal structures. We can look at physical models of these, or we can use models on our computers. And we have some that are available on mobile devices and some that are available for computers. So you can go on and look at some of the animations that you've seen in this video in more detail, and you can control them and you can rotate them and you can look at the structures in more details. So these are available for computers with full screens and also for tablet and phone side screens.